So I keep this separated. 5.4 was about samples. 5.5 is about like binomial probabilities and binomial distributions. And again, if you take a look at the formulas we use, they're going to come back and we're going to visit them again. If you look at the bottom of this page, I think I might have this here. This kind of tells us what we're looking for. We do these two tests. And we kind of visited this a little bit, but because our use in 4.2 was to do this when we had a large number, this test didn't really mean anything. But because we had large n's and we didn't want to put it in our calculator. But now it means something in this part. In order for us to be able to use a normal distribution to approximate a binomial one, it has to pass these two things. It has to say, remember, n is how much in your sample, and p is the probability of success. It has to pass these two things. If I take n times p, it has to be greater than or equal to 5. N times q has to be greater than or equal to 5. And the reason we do that is because of this. If you look at that graph on the bottom of that page, here's an n of 4. I only have 4 in my sample. N times p, whatever the probability is, came out to be 1, which is less than or equal to 5, right? This is less than or equal to 5. This is less than or equal to 5. Does this approximate a normal curve? Does that look like a normal curve to you?
No.
Where's the skew? Which way? To the right. It's kind of a little bit skewed to the right. So we need to say n times p greater than or equal to 5, n times q greater than or equal to 5. Okay, here's another one. N is 10, but my n times p is less than 5. My n times q, this guy's greater than or equal to 5. It means my probability was probably small, but my 1 minus my probability, my q, was a little larger. So this guy passed, this guy didn't. With me so far? Okay, so is this a normal curve?
No.
No, where's the skew?
Right.
To the right a little bit still, right? Still a little bit to the right. So we can't use this means we cannot use a normal distribution to approximate a binomial distribution. So for those first two, we stop right there. We say, do whatever you like, but we can't use this problem. This guy says n is 25, my n times p is greater than or equal to 5, my n times q is greater than or equal to 5. Pretty close to a normal curve, right? So this one says, yeah, you're pretty good now. You can use this theory to do whatever it is you like to do. And this one too. My n is 50, a little higher, and these guys came out higher. This came even closer together here. Didn't it get a little closer? A little higher? So it has to pass those two tests for us to be able to use a normal approximation, a normal distribution, to represent a binomial distribution. Okay? So that's why we do all this. That's why we do that test. Just so that you have a good understanding of why we do that test. And all we have to do for us, we're not graphing anything, we're just doing two little things. N times p is greater than or equal to 5, n times q is greater than or equal to 5. So in a survey of 8 to 18-year-old heavy media users in the U.S., we're still talking population here, 47% said they get fair to poor grades, C's or below. You randomly select 45 from this age group in the same heavy media users in the United States and ask them if they get fair or good grades. So we want to know, can we, first, we're not doing any work on it yet, can we use your normal distribution to approximate a binomial distribution? So we have to pass these two tests. That's all we want to figure out so far. We'll get to use them in a little bit, but all we want to do now is to see, can we use a normal distribution to approximate my binomial distribution? So we take out the n. In this case, the n is 45. What's the p? 47%. Therefore, q is 1 minus this. So what's q? 53. Good. So all we're doing is this. 45 times this. Is this true? Then we're saying 45 times 53. Is this true? If both of them are true, and in this case they're both true, this is true, then we can use a normal distribution to approximate your binomial distribution. If it's not, we stop there, because it's not gonna look like a normal curve. So those are the only two tests that we have to do, just to see if it approximates the normal distribution. Now, generally, you're going to see a pattern here. You're going to see that if your probability is low and your n is small, you really, really want to test it because you probably aren't going to make it. So the first one passes and the second one, no. So let's try the second one. The second one says, in the survey of 8 to 18-year-old light media users in the United States, 23% of them said they get fair or poor grades. These are below. You randomly select 20 of these light media users ages 8 to 18, and you ask them, did they get poor grades? They say yay, nay. Binomial, yes, no. This time, your P is 23%. Your N is 20%. It's 20. Now, sometimes when N is small or Q is small, it's not going to work. So your Q here is 1 minus this guy. If one of them fails, you don't have to test the second one because you can't use it. So as soon as you get one that fails, so what I do is I always test the smaller probability. Because if the smaller probability passes, doesn't the larger probability have to pass? Right? You're multiplying by a bigger number. So the smaller guy is this guy. And this comes out to be 4.6. This does not pass. The second one's going to pass, but I don't care because this one failed. So I say, sorry, I can't use my normal distribution to approximate your binomial distribution. Can't do this problem. Can't go any further. No matter what information you give me, I can't go any further. Okay? Now, in the book, of course, as we do the work problems, if they're going to pass, otherwise we have no work to do. So we're going to still test them, and we know they're going to pass because otherwise they wouldn't give us that problem to do. So that's what we're looking at from here on down. Now, once it passes, you can find your mean, and you can find your standard deviation. So let's take a look at one more, and just take this and find our mean and our standard deviation, if it passes. Excuse me. So in a survey of adults in the United States, 34% they have seen a person using a mobile device walk in front of a moving vehicle without looking. I can tell you how true that is. I was in the city yesterday, and people literally are on their phones walking into everything. Like, it's amazing. Amazing.
Where in the city were you?
I was around 8th Avenue and 42nd Street. I was in, like, Times Square area. You were there too?
Well, not exactly there, but I was in like the middle.
We went, my daughter was looking at wedding dresses. So, and then we went to eat at BBQ. That's like her favorite place. She likes those sticky wings. They're like humongous wings. They look like individual chickens. Think about. But people literally are just walking on their phones, even wheeling carriages and things and carrying. They're literally on their phones all the time. Or they're just walking into their car. They get out of their car. They call on their phone and they stand there. I'm like, pull your door, for goodness sake. This is serious. It's serious. In a survey of, and my daughter has like this much patience in her life, in her body, this much patience. So she's like, what, are they kidding me? Yeah, I'm like, are they you're in the city. But, yeah. So in the survey, 34% said they have seen this happen. You randomly select 100 adults. Now, it's going to work. Why do you say that?
I know it works.
Okay, because what's catching your eye? The N or the P? The 100. The N is pretty high, right? So especially when you multiply by 100, you're just going to multiply and move your decimals. So that's going to end up working for us. But the N is pretty high. If the N is low and the probability is low or the Q is low, that's questionable. So when we do this and we check these answers, we say N times P, and yes, it is greater than or equal to 5. It comes out to be 34, right? I moved the decimal. It's 3,400. Yep. Now, if this passes, and obviously this guy's got to pass because I'm multiplying by a larger number, so I'm okay there. This automatically is my mean because your mean is N times P. So you're halfway through the problem. So your standard deviation would be the square root of N times P times Q. So if you took this piece, 34, and then multiplied it by your Q and took your square root of that, you would find out your standard deviation. So once it passes, you already have your mean. N times P is your mean. So all you have to do is multiply that right underneath your square root sign. So your standard deviation would be about 4.74. Okay? So we're halfway to getting through the problem. Questions? Now see, why do we do all this? Okay. Now, before we can start with our probability statements, and before we can use our z-score, we have a little logistics problem here. So if you turn to page 277, they give a very nice diagram here, and I don't think I have this diagram. I should, but I don't. They give a little bar. Now, what happens is this. Here's our normal curve. We said our normal curve is a series of bars, right? And they make the shape of a normal curve. These numbers are discrete numbers in here. Discrete meaning there's no decimals in there. So technically there's no bar in there. If I have one person, two persons, three persons, four persons, I take, frequencies, whatever, it's just a line. If I make this 1, 2, 3, 4, whatever, these guys are just lines. They're not bars. They're lines because there's no decimals in here. So if you look at their diagram, you can clearly see on page 277, your exact binomial probability is exactly that. They say x is equal to c, any number, meaning any whole number. Your probability says, well, I need a bar here. It's my area under my curve. I need this little bar. Because my probabilities are from 0 to 100, decimals and everything else in there. But the discretes say, you got a problem here. So to get around that problem, we do this little thing called correction for continuity. Now, all that correction for continuity says is, so say this is a 4, and there's a 3 here and a 5 here. I need to expand this bar so that it meets the 3.5 and the 4.5. And then this 3.5 meets the 2.5. And then this 4.5 meets the 5.5. I just need to expand that bar. Because right now, I'm not touching. I really can't make a continuous curve out of this. If you think about it, they're discrete numbers, and we touched on this a little bit in chapter 4. They're discrete probabilities, discrete versus continuous, right? So we just need to expand this bar. And we kind of did it a little bit in chapter 4. We just took this number and we dropped it, 0.5, and on the other side we added 0.5. Remember when we changed the probability statements? We dropped the 0.5, we added it 0.5. So we're going to do the same thing here. We have a correction for continuity. Because we have to put this on a continuous curve, if we're going to find out that this makes a normal distribution, I have to logistically say, expand this little bar. Kind of like, remember about I talked about your air conditioner? You put your air conditioner in the window and you got a gap, and you have those little sides, like those little accordions that come out. All we're doing is pulling the little accordions out, making them fit in. Same thing we did in chapter 4, but I think it makes a little bit more sense now. So all we're going to do is subtract 5 from the lower end, add 5 to the higher end, just like we did in chapter 4. But this one has a little bit of a twist to it. You have to look to see what your statement says. So I have to look at my probability statement first and then correct it. So my probability statement says, what is the probability of getting between 270 and 310 successes inclusive? Don't forget, these are whole numbers. I want 270, 271, 272. I start like this. I want all of these, dot, 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 309, 310. I want to include these guys. So my rule is, I'm going to drop 0.5, subtract 0.5 from the left end, and I'm going to add 0.5 to the right end. Just like we did in chapter 4, but we just did it to a statement, and we really didn't look at the graph as much. So now, instead of my probability statement looking like this, inclusive means we include it. Oops, 310. We're going to have to take this number and drop it down 0.5. If you remember back, we said it doesn't affect your probability statement because we never had a number 270.5, right? We're either going to get a 269 or a 270. Will I count 269 in here? Nope. Will I count 271 in here? Yep. So all this does is move my bar out there to make me have a continuous graph. And so this guy, I can say 310.5. Will I ever find a 310.5? Nope, because I have discrete numbers. I have whole numbers. Will I find a 310? Yep. So this is key because these are your x values. These values are going in this formula. So when I take this now, instead of putting in 310, I have to put in 310.5. Not a major hit, but if n is small, I notice it a lot more. If n is large, I don't notice it as much. So we have to determine, are we looking at a lower end? Are we looking at a higher end? This probability statement says the probability of at least 158 successes. What is at least in terms of an inequality sign? Less than or equal to, greater than or equal to, not equal to. I have at least $3 in my pocket. Greater than or equal to, that is the least it's going to be. So this is how we start. The first number I could have is 158, then 159, then keep on going, right? So do I have a lower end here or an upper end? A lower end. So what is my rule? Subtract 0.5 from my lower end. I have no upper end. So I'm okay. So here's my correction for continuity. Will I ever hit a 157.5? No. What's the first number that I will hit? 158. And isn't that what I want? 158. So why do I do this? Because it's a little bit more area underneath my curve. My curve right now, when I take my binomials, says 156, 157, 158. If I start here at 158, I'm only getting these guys. 159, 160. I don't have any bars in between them. So to make this, I drop this one right here, and now I can make my normal curve. And you only have to do your endpoints. Obviously not individual points. But you only have to do your endpoints. Probably doesn't make sense yet, but think about it this way. Discrete numbers are whole numbers. What kind of number is in your normal curve? What is that number line? Is that a discrete or a continuous line? When I make my normal curve, is that a discrete number or a continuous line? Okay, so last week we said here's a mean, 270, here's a standard deviation, 5.2. So I add 5.2. I added 5.2. Oops, sorry, 270. What am I doing? 275.2. Is that a discrete number? 275.2? No. So didn't I have all kinds of numbers on my curve up to then? Didn't have to be discrete. Didn't some of my standard deviations come out with decimals? Didn't some of my means come out with decimals? Do I get any decimals when I count the number of successes when people say yay, nay? Do I get a half of a yes? These are all whole numbers. These were all mixed in because your number line is a continuous number line. These guys are not a continuous number line. They got little pieces. They got all of the whole numbers. They have none of the decimals. So to make up that slack, I got to expand those bars. And the only bars I care about is the beginning and the end bars. So that's where we correct this for continuity. So one little step before we can do our z-score formula. Okay. What is the probability of getting less than 63 successes? So I start. I probably had started at 0. 0 successes. 62. 63. Can I use 63? Is 63 less than 63? Nope, so I can't use this guy. So my last thing I can do is 62.5. Okay, I gave you the answer. It's 62. So am I on the upper end or the lower end? The upper end. So my upper end says 62.5. So all I do is change this to 62.5. Will I ever hit a 62.5? Nope. And then less than 63s, I'll still never hit one. The first number I hit is 62. But if I start my curve here at 62, and that's 62.5, I missed this little piece in here. I just missed that little piece of area. And area is part of your probability. It's area under your curve. Okay. Sorry, I slipped and gave you that answer. So kind of just, I find it easiest when I lay them out. Lay out where you start, where you end. Subtract 5 from the lower end, add 5 to the upper end. It's just like expanding that last bar. So I'm going to have you try a couple of these. That's only 2. So I'm going to have you try these guys. So the first one. Probability of getting between 57 and 83 successes inclusive. So Carlos, what does that probability statement look like?
67.
Mix it now. Less than or equal to? 83. So now, if I start like this, I include 57, 58, I include 82, 83. So what does your correction one say? What's your correction one say? 56.5. You're dropping it down. 83.5. Good. Now, when you do this, this is a key word, inclusive. What if this did not say inclusive? What if it did not say inclusive? Sarah, what would it look like if it did not say inclusive? Just to begin with, without the correction in there. Oh, okay, without the line, we can do that. Good. So what Sarah did, she said she put this statement in, shouldn't have an equal sign in here, not including this. So do I start at 57? No, I have to start at 58, 59, go all the way up, 82, 83. Am I using 83 if it's not including it? if it's not inclusive, I can't use 83. So my last number is 82. My first number is 58. I can't use 57. Not inclusive. So I drop down the 58 to 57.5. I raise the 82 to 82.5. Good? Okay, probability of getting at most 54 successes. So Angelique, how do I write my beginning statement? What's an at most? It's the opposite of the at least. So what inequality sign do I put? Less than or? Good. Think of it this way. If we go shopping, you say, can I borrow $10? I said, well, I have at most $10. So am I going to be able to give you $10 if I have at most $10 on me? At 10 or more, right? So you're in luck. I get to give you my $10. So now, it goes like this. It stops at 54. I include 54. Correction for continuity. Do I have a lower end or an upper end? Upper. So how would I correct this for continuity? 54.5. At this point, this greater than or equal sign doesn't really matter here because you're never going to be equal to a 0.5. You're discrete numbers. So I tend to write the equal sign. I don't know. I don't think the book does. I don't think the book writes the equal sign. But I tend to write it, but you're never going to be equal to that anyway. So you don't have to worry about writing the equal sign, actually. I don't think they write it. Now, underneath this guy was a little chart. So if you have trouble, reference your chart. Inclusive does not include how they write more than, less than, at most. But I find a chart harder to understand than just doing the numbers out in person, but that's how the chart goes. Okay. Any questions up to now? Okay. I'm going to give you guys a little assignment that you're going to have tomorrow. Tomorrow we're going to talk about your project, but you're also going to have tomorrow to work on this. Probably like 10 minutes. It won't take you long. It looks like a lot, but a lot of them are matching. So tomorrow, first 10 minutes when you come in, we'll do it. Then we'll go over it in 5 minutes, and then we'll talk about your project. The only difference with this thing is it's discrete. And that's what I need you to get a hold of on this one. Our curve is continuous. All the area under the curve covers every number from left to right. Every decimal. And we've been using decimals, haven't we? For means and for standard deviations, we've been using decimals. In these, we can't use decimals because it's discrete. It's countable. People that I asked in a survey, do you say yes? Do you say no? You don't say, oh, I'll be a half a person right now. I'll only give you a little yay. So we have to change this. We just have to modify this a little bit.